Hello everyone. Hope everyone is doing good. Today we are actually going to find the expression for stresses on oblique plane. I'm not sure if the pronunciation is oblique or oblique. I can safely say we are going to find the stresses on inclined planes. So why these concepts are important? These concepts are important to build the theories of failure, to understand theories of failure, which are very crucial for a structural engineer. We have to understand the concept of stresses on inclined planes. So we will take this very slowly, very gradually. So first we will consider a simple rectangular member that is subjected to load on one direction, okay? So just imagine that you have got a rectangular member. So what I mean by rectangular member is, well, it's just a rectangular structure. Of course, it's three-dimensional, which means it has got a certain thickness. We can say that along the z direction, the thickness is t. Okay. Now, this rectangular member, the structure, is subjected to a load on either side. So say for example, it is subjected to a pull. So it is subjected to a pull on either side, and the magnitude of the pull is capital P. The force that is acting, it is capital P. I can define stress safely. Say for example, I can simply say stress is load divided by cross-sectional area. The cross-sectional area is, say in our case, it is the height into thickness. So let me mention that very clearly. The cross-sectional area is the height, well, it is this distance into thickness. Thickness is measured along the z direction. So I can say, let us say that this is AB. So I can further write this formula as load divided by the length AB into thickness. So that is the cross-sectional area. Okay. Now, a little consideration. Now, you can ask a question. Why do you always define stress with respect to this cross-sectional area? Why not try to define stress on an inclined plane like this? Okay. So we are going to do exactly that. We are just going to define what is the stress for an inclined plane. Okay. Well, we failed to ask that question. We could have asked this question. Why not try to define the stress with respect to this plane? Say, for example, this particular plane. Okay. Why not? Now, we will now try to define stress with respect to this particular plane. So look for yellow color. So I'm just going to define stress with respect to this plane. Okay. So let me localize my attention on this plane. Maybe I can draw this plane separately for my convenience. Okay. Say for example, this is AB. Let me call this as C. And let us say that the angle is theta. Okay. Now, let me represent the blue line also, the line AB here. Okay, so here is our line AB. It's a simple concept actually. Okay, this is our line A, this is the line, okay, this is B, this is C. Okay. Now, according to principle of transmissibility, the load that is acting, which is represented by the red arrow there, can be assumed to act throughout the line of action, which means the load is acting in this direction too. Now we are going to resolve this load into two components. Okay, so before I even do that, let us say that this angle, as I told you, it is theta. So what do you think is going to be this angle? It is also theta. And what about this angle? It should be 90 minus theta. So it is 90 minus theta. Okay. So I don't want this diagram to look very cluttered. So what I will do, Let me erase it. I know that this angle is 90 minus theta. So let me safely write this is 90 minus theta and the load is capital P. Now I'm going to resolve this load into two components. One is the horizontal component, another one is the vertical component. So what is the horizontal component of this load? This is the horizontal component of the load, which is actually P cos 90 minus theta. And what is the vertical component of the load? It is perpendicular. What is the vertical component? It is actually perpendicular to this yellow plane, and that is P sine 90 minus theta. We know that P cos 90 minus theta is P sine theta, and we know that P sine 90 minus theta is P cos theta. Okay, I'm doing this very slowly because I'm just thinking of what is the next step. Okay, fine. Okay, now I have two forces. One is the force that is perpendicular to this yellow, okay, I like this, perpendicular, which is P cos theta, and the force that is acting tangential to the yellow, which is P sin theta. Now it is quite obvious, it is quite axiomatic that the force that is acting perpendicular to the yellow should actually cause a normal stress with respect to the yellow line, with respect to the inclined plane. And the force that is acting tangential to the yellow, which is P sine theta, should actually cause shear stress along the yellow line, right? So now we have a very good reason how to compute the normal stress and the shear stress, all right? So that's what we are going to do in the next step. So let us try to define what is the normal stress, and let us try to define what is the shear stress, okay? So the normal stress on the oblique plane, the inclined plane, is the force, which is P cos theta, divided by the cross-sectional area, which is the length AC into thickness, okay? The length AC into thickness. That is the cross-sectional area, fine. Now I have to write what is this length AC, right? What is this length AC? So again, let us try to find what is this length AC. We know that this length AC, if you look at this, let us try to say cos theta maybe. Cos theta is adjacent side divided by hypotenuse, okay? In this triangle ABC, right? Let us try to define what is cos theta, which is the adjacent side, which is AB. It's a right-angled triangle, divided by the hypotenuse side, which is AC. So that should give me what is the value of AC. AC should be equal to AB divided by cos theta, okay? Hope that works. Okay, mathematics is just like moving objects. All I have to do is I have to take this value of AC and I have to substitute it here. So the normal stress is equal to P cos theta divided by AC is AB divided by cos theta. I can take this cos theta to the numerator. It becomes cos squared theta, cos theta into thickness. We already know what is AB into T, and that is cross-sectional area. So in the next step, the normal stress is P cos squared theta divided by A. So now I know what is this P by A. P by A is simply the normal stress, okay, sigma, the usual stress that we have defined here. It is the sigma. So I can just take this value of sigma and I can plug it here. So the normal stress on this yellow line is sigma into cos squared theta. Well, I got the expression for the normal stress. Well, good, fine. I hope I didn't struggle that much. Okay, now the expression for the shear stress. Okay, fine. Now let us try to find the tangential stress, which is the shear stress. So I will just add the suffix T as shear force, which is P sine theta divided by the cross-sectional area, which is AC into thickness. Okay. And the next step, it can be written as P sine theta divided by, we know AC is AB cos theta. So if you just plug this value here, so you'll be getting AB divided by cos theta. I can take this cos theta to the numerator. So cos theta into thickness. Again, this AB into T is simply cross-sectional area. So in the next step, it's going to be P by A into sine theta cos theta, which is sigma into sine theta cos theta. In the next step, the tangential stress is, I'm just going to multiply and divide by 2 in the numerator and the denominator, so I'm not going to do any damage to the equation. So let me multiply by 2. So it becomes 2 sine theta cos theta divided by 2 times 2. Yeah, that is 2. That's right. Fine. So in the next step, what is 2 sine theta cos theta? It is sine 2 theta. Okay, so it is equal to sigma divided by 2 into sine 2 theta. Let me use a different color to tell that we got the expression for the tangential stress. So that is it. So we now have 2 expressions. One is the expression for the normal stress, and another is the expression for the tangential stress. The expression for the normal stress, as you could see, that it is sigma into cos square theta, and the expression for the tangential stress, it is sigma by 2 into sine 2 theta. Okay, fine. Now, let us push the equations to their extreme. Now, at what stress, at what value of theta, the value of the normal stress is going to become maximum? Okay, let us try this. Now, this is the expression for the normal stress that we have got. It becomes maximum at what value? It becomes maximum when the value of theta is equal to 0 degree, or it can also become maximum when the value of theta is 180 degrees. So there are 2 values at which this is going to just become maximum. When the value of theta is equal to 0 degree, it's just going to become maximum, right? So when do you think this theta is going to become 0 degrees? So let us work this out. So this is theta. It's at a certain angle. So now this becomes 0 degree right here. Okay, the theta value decreases. It decreases with respect to the blue line. It decreases, and reaches 0 here. Okay, so it's going to become maximum. The maximum normal stress is on the plane, on the blue plane, which means all the planes that are perpendicular to blue planes will be experiencing the maximum normal stress. So let me write that. All the planes that are parallel, not perpendicular. Did I use the word perpendicular? I'm sorry. All the planes that are parallel to the blue are going to experience the maximum normal stress. Okay. What about the maximum shear? Okay, the plane at which the theta becomes maximum, which means theta should be equal to 45 degree, right? Only then this 2 theta becomes 90 degree. We know that sine 90 is maximum 1. So theta should be 45 degree. So this angle should be 45 degree, which means maybe I can use a slightly different color here, the green. So say green. All the green, okay, yes, the green, which is at an angle of 45 degree, let us say that the angle, let me get rid of the scale, let us say that this is 45 degree, okay. All the planes that are at an angle of 45 degree, they will be experiencing the maximum shear. Okay, good. So now we know the planes that are experiencing the maximum normal stress, which is the blue planes, and the planes that are experiencing the maximum shear stress, the green planes that are at an angle of 45 degree, okay, that will be experiencing the maximum shear stress, okay. And what about the plane, at the blue plane, what is the value of the shear stress? Well, there is a pattern that is coming now. That pattern is when the normal stress becomes maximum, that is when theta is equal to 0 degree. So the plane where the maximum normal stress exists, at that plane, if you try to compute the value of sigma t, which when you put theta is equal to 0 degree, then sigma t becomes 0, which means that the planes, there is a pattern that is coming. The pattern is the planes that are experiencing the maximum normal stress are going to experience 0 shear stress. And those planes that are experiencing the maximum normal stress and where there are 0 shear stresses are called as the principal planes. And that stress is called as principal stress. So in our case, the maximum normal stress, it is the principal stress, and the plane on which it exists, it is called as the principal plane, which is the blue plane AB, right? That is the principal plane. And at that plane, there is 0 shear, okay, which is an important concept, okay? Now, why this is important? Now, when you're doing a tensile test experiment, let us take this particular case, and when you're doing this tensile test experiment, now just let me draw a separate specimen here. This is the tensile test specimen. Doesn't look like one, so this one will do. Yeah. Yes. Now this is the blue plane, which is AB, and the yellow guy is here, which looks like this. Okay, this is C, and we know that the green is going to experience the maximum shear at an angle of 45 degree. Okay, all the greens are experiencing, and all the blues are experiencing the maximum normal stress. Okay, fine. Now if you take a brittle material, right, the brittle materials will always fail at the blue plane, which means that they are going to always fail when the value of theta is 0 degree. Okay, the brittle materials are going to fail. What about the ductile materials? You see that the ductile materials, they always fail at an angle of 45 degree. They always fail at an angle of 45 degree. Okay, the other angle is 135 degree. In both 45 degree as well as in 135 degree, the value of the shear stress becomes maximum. So either it is 45 degree like this, okay, or you keep increasing, then it becomes a maximum, and then it reach 135 degree, okay, 135 degree on the other side. So at that plane also experiences the maximum shear. So it is 45 degree, so this is 45 degree, and also 135 degree. Okay, the plane goes like this. Okay, which means that the brittle materials always fail at an angle of 0 degree, and the ductile materials, they always fail at an angle of 45 degree, which means that the materials, let us say that the material is going to fail here, right, at an angle of 45 degree, which means that there is a necking that should form like this, okay, at an angle of 45 degree. If you just measure this value, right, this is 45 degree, this is 45 degree, okay. So there is a necking that forms. So whenever you see neck formation, it happens because in the case of a ductile material. So now we can safely conclude that the brittle materials are actually going to fail due to the normal stress, and the ductile materials are actually going to fail due to the maximum shear stress. So this slowly is going to take us to the theories of failure. It's a very simple concept. Maybe I have dragged it a little bit. Allow this concept to sink in naturally in your mind and think about it. If you're already familiar, we can, yes, in the next video we can delve deeper into the topics of failure theory. So thank you all for your patience. Enough for today. Thank you so much.